Okay, today we're going to dig a little deeper into potential energy that we talked about last time, and we'll introduce a new concept, force. So we learned last time that energy, total energy, which is a conserved quantity, can be thought of as being distributed into kinetic energy, which is energy to the motion of the particle, and potential energy, energy due to the position of the particle. So if we look at potential energy, and we were to sketch a graph of energy on an energy versus position plane, we will see any kind of crazy curve here could represent the value of the potential energy as a function of position. And so what we want to do is let's consider a particle sitting at some position x, and we're going to move that particle an infinitesimal amount, just the smallest amount, to position x plus dx. So imagine dx being infinite, an infinitesimal distance. And then what we're going to do is figure out how much does the potential energy change here. And so we're going to be looking at the dV. Now, logic would tell us that there's really three choices, right? We could go up in potential energy, we could go down in potential energy, or we could stay the same in potential energy. More mathematically, this would be dx could be positive, negative, or zero. For those of you who've had some calculus, you recognize what we're looking at here is the derivative of the potential energy. So the spatial derivative of the potential energy. Now it turns out this is a very important physical property in its own right, as one maybe would expect because energy itself is such an important concept. More specifically, the negative, and that's just for convention, the negative of this derivative is what we call force. Now we've cheated a little bit here because potential energy is a scalar quantity, meaning it just has a magnitude, whereas the force is actually a vector quantity, so it'll have a magnitude and direction. So this can't quite be right here. But in order to fully understand that, we need some concepts from Calculus 3. And so in this introductory course, we're not expecting that you would have had that. But I'll just state what the real definition of force is here. Force is a vector, and it's obtained by taking what's called the gradient. This is you could think of this as a 2 or 3 dimensional derivative depending on what space you're in. If we're in all of our space here, then it would be a 3-dimensional derivative, and it results in a vector quantity. Maybe giving just an example. Imagine I'm standing on some kind of hill, right? I have some potential energy because of my position on that hill. Maybe if I walk in this direction, I don't go up or down too much on the hill. Maybe I step in this direction, I go down just a little bit. And then if I step off in this direction, I go down a lot. This shows what the gradient is the direction for which I would drop the most. Well, the negative of the gradient is the direction I would drop the most. So I don't drop very much here. I don't drop very much here, but I drop a lot here. So that means my force vector would be in this direction, and the magnitude, the length of that vector, would be how much I actually change. So if I drop a whole lot, then it's a really big vector. If I drop just a little bit, then it's a very short vector. Okay? So we have to reconcile the fact that force is a vector, which we'll be using a lot in the coming days. All right, well, let's just categorize some types of systems based on their potential energy and therefore the force. So the simplest one is when potential energy doesn't change. So potential energy, maybe it's a constant, maybe it's zero. In either case, it doesn't matter what position we're in. So if I put my particle here, the potential energy is the same. And so we think about how does that change if we move it? Zero, right? And if you've had some calculus, you know that the derivative of a constant is zero. And so our force equals zero throughout that whole system. The type of system we call that is a free particle. And it undergoes what's called uniform motion. And motion, we'll be definitely getting into motion very soon now. Motion could mean standing still. So we'll talk about that in more detail. So it's a constant velocity. That velocity could be zero, or any other constant velocity would fall under this category of potential energy, constant potential energy, zero force. All right, well, now let's look at the next simplest is when the potential energy is linear. So we make a graph here, linear potential energy, right? Slope of A. Well, if I'm here and I go here, that's my change. So in this case, this derivative or this change is positive. The force is defined with the negative. It changes by the amount of the slope, A. So my force then is negative A. So I graph my force. It's a constant, right? Because if I go to another spot and make that little change, it's the same, right? Because this is a straight line of constant slope. Again, if you're in calculus, this should be one of the first derivatives you learned, derivative of x, and so it's just A, and then where's the negative sign coming from again? That's from the convention here, negative. All right, well, we've done constant, linear. Let's do quadratic. I wouldn't have had to put the 1/2 here, but just for convenience, I'll do that. So this is a x squared, so we remember that as a parabola. So here's our picture of the potential energy versus position. So if I'm at the base of that parabola, or the bottom of that parabola, then I'm at my lowest potential energy. If I go in this direction, I go up. If I go in this direction, I go up. If I'm sitting at some arbitrary point, here, I make a little move here, then I go up. Oh, and I see a mistake here. I'll redraw this. So if I'm on this side, I'm always going up. If I'm on this side, I'm always going down. Now we have to take into account the negative sign. And so let's sketch the force. Well, we don't know for sure until we've had some calculus how this is going to look, but our force is going to be positive over here because here we're going down. And so we will get a curve that is positive 0 here, because if we make an infinitesimal change right at the base, we don't really go up or down. So that's where we cross 0. And then over here, we're going up, so we're positive. The negative sign convention then puts us negative on this force axis. Now, if you've had some calculus, you know when we take the derivative of a quadratic here in this case, or anything with this power, that will come down here. We draw that down and we reduce this power by 1. And that's why that was the motivation for using this half. So this will come down, cancel there, and leave us with kx. Well, and then the minus sign is our convention. So for this case, so a second order or quadratic potential energy, we get a linear force. These systems are called spring-like, and the type of motion is oscillatory. I think I'm not remembering if I went through this part, so let's back up. Here we've got linear potential energy, constant negative force. The type of system we call this is free fall, and the most immediate one we are used to is just an object dropping towards Earth. So my object undergoes free fall. That's what we mean by this. More chemically, and what we'll see later in the course, is if we have, say, a charged ion right by a charged metal plate or an electrode, that will also be a free fall situation. And that's constant acceleration. All right, so let's think about this sort of systematically. Constant, linear, quadratic. Zero, constant, linear. And then the system is a free particle, uniform velocity. Free fall, constant acceleration. So constant velocity, constant acceleration. And now interestingly here, we get oscillatory motion. So if you think about what most things in nature do, right? They're either going to sit still, they're going to move with constant velocity, they're going to accelerate, or they're going to oscillate. Now, of course, this doesn't capture everything, but it captures an awful lot of stuff with just three different mathematical forms or functional forms for the potential energy. All right, well, this concept of force is going to be very important, as I mentioned, and it in fact forms the basis for what are called Newton's laws, which is what we'll launch into in the next few days. And we will see that force will control or determine the dynamics of a particle. And this is called Newtonian mechanics. Now, there are other ways, as you might well expect here, because force is related to energy, there are other ways to formulate dynamics based on energy, but those are more advanced, and we'll hit those as we're out of these introductory courses into the more advanced courses in physical chemistry. So force will serve as our key fundamental property that will determine how objects move. And so we'll launch into that shortly.